Good Thursday morning. What is it, Zach? March 19th. So, good morning. Welcome to Carlson Chem Session 3, Acid-Base Equilibrium Continued. Thought I'd have a little fun, get a little blast from the past. Step back a little bit here. So I was just in my my mom's home in Peoria, Illinois this past week for not the best reasons. My mom did actually pass away, but spread all over the house were pictures. So this is about 1976, I would say. So you can try to figure out who's who there. Can they see that?
Yeah.
So there you go. There's me and my siblings back in 1976, I would say. So you can figure out who's who there. It's my two brothers and my sister. So anyway, little blast from the past. I'm the if you couldn't figure it out, I'm the best looking one. The youngest boy there. So anyway, hope you are keeping the important things important during Corona, right? So I figured out we got the 3 C's during Corona. So keep these straight. All right, during Corona, the 3 C's, you got to stay calm. Everybody's just got to stay calm. And be clean. You got to be clean. Stay calm, be clean, and then, of course, do chemistry. So, the 3 C's, don't forget those. All right. I do hope everybody's well. If you need anything, you should make sure you're letting those around you know. So we can help each other out. So I did get directions from Principal Snookhouse on how we're going to proceed with all the other classes, which will roll out on Monday. Hopefully, I'll be able to keep doing this platform for AP. We'll be doing Edgenuity, it looks like, for all the other classes. But I do hope that we can continue this platform. I think there's a little bit of flexibility with AP courses. So, but this was under the radar of the district and just something I'm doing. So hopefully it's helpful and we'll continue. I know the numbers dropped dramatically from day 1 to day 2, but we'll see if they pick up again and see if it's helpful. All right, we're going to jump in here to, if you take out your notes on acid-base strength, where are we at here? Page 9, actually. Starts off by talking about structure of acids and bases. Page 9, structure of acids and bases. And again, the very top equation that I wrote here, this very top one, above the dash here. This is, again, what happens with an acid or a base, but in this case an acid. We have nitric acid, which does end up being a strong acid. If it's a strong acid, we have complete dissociation. And when we have complete dissociation, we have only one arrowhead to the right. And so the nitric acid gives up a proton, gives up an H+. And when we talk about H+ being a proton, that means if you think about hydrogen, there isn't a neutron, and hydrogen has 1 proton, 1 electron, so if it's H+, it gave up its electron, so it's only a proton. So when we talk about being a proton donor, that's literally what's happening. H+, has given up its electron, so it's literally just a bare proton, which is what makes it so powerful. So nitric acid in the presence of water is going to give up this proton, this H plus, to the water to become hydronium, H3O plus, because it has an extra hydrogen, and then the anion, NO3. So again, in terms of conjugates, you have to be very well versed in understanding that if this is my acid, on the other side, what's left after the hydrogen is given is its conjugate. And we talk about conjugate acid-base pairs. So if this is the acid, its conjugate is the base. If this is strong, if this is a strong acid, which it is, its conjugate is weak. And because it's like that's how the whole thing works, is because this is weak, it's not picking up the hydrogen again to reform the original acid. It's staying separate. So floating around in the solution, we have a weak anion, but we have a strong cation, because this was a strong acid, but water is not a strong base. It's a weak base. So if this is a weak base, its conjugate is strong. All right, so that's just kind of talking about the general acid-base realities here. And then the next part of the notes talks about relative strengths of weak carboxylic acids. And I was starting to write out the three, so on your notes. So Zach, if you scroll down to page 10 to the chart on the top.
One of your students needs to use the restroom.
Oh, okay. Go ahead and use the restroom and come back and I'll still be talking.
Adam wants to know if you found a cure for the virus yet.
Not yet, but we're working so hard on that. No, that's not. I don't want to joke about the virus. It is very, very serious business. But jokingly, I could say, yeah, we're working real hard on it. But the reality is that I can't even imagine how hard the top labs are working on it. If I had that many brains, Adam, I would definitely be working toward a cure. Thanks for the question. Propanoic acid, if you look at your chart, propanoic acid is at the top. I'm not writing that out, I don't have room. Propanoic acid, ethanoic, and then methanoic has just the hydrogen attached to the carbon, a double bonded oxygen, and then our single. So I just want to talk a little bit about acid strength and what happens with these. These are all considered carboxylic acids, and you can read the text in the notes here. But what makes an acid is the presence of this hydronium ion, this H3O plus. That's what the more there is of this, the stronger the acid is. The more there is of hydronium, the stronger the acid. Or let me say this, the easier it is to take this away. The easier it is to make this, the stronger the acid is. The more there is of it, we could talk about its concentration. So, it can potentially be confusing here because we have so many hydrogens. So when you look at carboxylic acids, they all have a ending carbon with a double bonded oxygen and then an oxygen with a hydrogen or a OH group, okay? So the hydrogen that's becoming available to make it an acid is this hydrogen. The hydrogen that's attached to the oxygen. That's the hydrogen that's pulling away to become an acid. All right. So the easier it is to pull this away, the stronger the acid is. Now, all of these carboxylic acids end up being weak. They're all weak. But we can still rate their strengths among them. So yes, they're all weak, but which one is the strongest of the weak, which is the weakest of the weak, kind of a thing. So these alkyl groups, you don't have to even know what that is necessarily, but these CH3 and CH2 groups end up being electron pushers, and they're pushing electrons over here, okay? And as they're pushing electrons, like the bigger this side is, the more electrons it's pushing. And if it's pushing electrons over here, it's making this more, this anion side more unstable, which means it's not going to drop off the hydrogen. So if there's more electron pushing going on, and it makes it actually less stable over here. If it's going to build up a negative charge, then it's going to keep the hydrogen attached, okay? So I don't know that you really even need to know all of that, except that you need to know the trend for carboxylic acids is the larger the chain gets over here. When it's just carbons and hydrogens, the larger the chain gets, the weaker the acid is. And so if you look at the pKa strengths on your chart, you see 4.9, 4.76, and 3.75, okay? Just like pH, if you think about acids, pH or acid strength, the lower the pH, the greater acidity, right? A pH of 1 is stronger than a pH of 3. A pH of 3 is stronger than a pH of 7. So just like the lower the pH, the stronger or the greater the acidity, the lower the pKa value. The lower the pKa value, the greater the acid strength. Because the lower the pKa value, the higher the Ka value. So as pKa goes down, Ka goes up. As Ka goes up, that means more of the hydrogen got dissociated. All right? So this is carboxylic acids. I think that one's quite a bit harder to understand than the next two pages here. If we go to page 11 and look at that chart there, Zach. So those who needed the restroom, here's a little 10-second break. All right. Any other questions? All right, so we have now ethanoic and chloroethanoic and dichloro. So let me just write these a couple of these out here. We have carbon, and then we're going to replace I gotta rewrite that one. Sorry, you're seeing the back of my head here, but I can't. I don't have. This would be just like if we were in class and I was writing on the board here. So that's better. And this. And okay, so here, what we're changing here is we're substituting chlorines for hydrogens. Okay, so I've only written 3 of these out. You have 4 on your chart. I put 3 up here. But this again is our ethanoic acid with no chlorines. It's got a pKa of 4.76. All right, again, in terms of acids, what's happening here to make this an acid in the presence of water? So let me do that. Let me say if we're gonna what's not on your notes? Yeah, go ahead.
So the longer the chain, the weaker the acid because there's stronger forces? Question.
Yeah. The stronger the, or the longer the chain, the weaker the acid, because yes, the forces holding the hydrogen in are greater, because we need that hydrogen to detach. So, good question. And if I didn't answer it, ask it again, or ask it in a different way if I didn't get that. So, back to here, before I put the pKa's up here, if we're gonna, in the presence of water, if we just look at this first one on your chart, on the top of page 11, what's happening to make this an acid, and it's a weak acid, so it's in equilibrium, is that we're taking this hydrogen away. So what's forming is everything else, like, if we just add up what's left, we have 2 carbons, 3 hydrogens, 2 oxygens, and there's lots of different ways to write that, but we have this anion. So if I just leave it like it is, but I'm going to write it smaller to fit it in here. Okay, we would have this anion, because it's all of this minus the hydrogen. So we have this anion, and of course it would be negative because we lost the hydrogen. Plus, so all of this would be negative, plus our H3O plus, right? That's what's happening with these acids, okay? And so the pKa again over here is 4.76. Okay, now, if we go from the top one to the second one, we see what happened is we replaced, if a hydrogen gets replaced with a chlorine, chlorine is much more electronegative. It's much more electronegative. And so that electronegativity, as we start increasing electronegativity, we start getting more polar. And the more polar we get, the easier it is to take this hydrogen away. And so I just put this down. So our numbers now are 2.86, 1.29, and then on your chart you see 0.65. So just like it says at the bottom of your grid there, this time the highly electronegative chlorine atoms attract electron density away, and so that increases the stability. So in this case, as we're adding chlorines, here we added 1 chlorine, our pKa got lower, so our acid strength increased. We added 2 chlorines, our pKa gets even lower. And so when you are ranking acids by acid strength, you've got your trend for carboxylic acids, which was on the first page we looked at, and now on this page, as you increase the number of chlorines, you are increasing acid strength. You're increasing the electronegativity over here. So then we can go on to the last page of this part of acid strength, and that's on page 12. And now we have ethanoic acid, bromoethanoic, chloroethanoic, and fluoroethanoic. And so we'll look at a couple of those. So now we're changing the alkyl group. So again, ethanoic, I don't know if I need to write this out. I can just kind of talk through it. Hopefully, if you look at your chart, on ethanoic, we don't have any alkyl group. There's no halogen group. There's no halogen group in ethanoic acid. They're just hydrogen, hydrogen, hydrogen. If you look at bromoethanoic, one of the hydrogens has been replaced by a bromine. Chloroethanoic, one of the hydrogens has been replaced by a chlorine. And fluoro, one of the hydrogens has been replaced by fluorine. And if you remember electronegativity from the periodic table, fluorine is the most electronegative. So the increasing acid strength then is increasing with increasing electronegativity. So the pKa's go down from 4.76 to 2.66. So why do we go over this? It's rather common to see ranking questions for multiple choice. Could even be free response. Rank the following acids by strength and so forth. I'm sure, I would imagine there's some ranking questions in mastering chemistry, and I'll be populating mastering chemistry pretty soon here, today or tomorrow. But ranking, why would you need to know this ranking? If they give you pKa if they give you Ka values, then you need to absolutely know the greater the Ka value, the greater the dissociation. The greater the dissociation, the more hydrogen ion there is. The more hydrogen ion there is, the stronger the acid is. At the same time, you need to know the relationship between Ka and pKa, right? The greater the Ka value, the lower the pKa value. So if you're looking at pKa value, like if they give you pKa values and you're ranking acid strength, you're picking the lowest pKa value, which corresponds to the highest Ka value. All right? That's just the math of it with logarithms. Do we have a question?
On the answer key you sent with the Kristen Jones packet, you left problem 3 and 4 blank. They're wondering if you can work them out and send them over remind after the video. Okay.
Yeah, I mean, I can do that sometime later today. Good off-topic, off-point question. Good, and that's a good interruptive question. So yeah, we can absolutely do that. I can work that. So that's Kristen Jones. What was it? Kristen Jones, page 3.
Problem 3.
Problem 3 and 4. Okay. I should probably need to write that down. So Kristen Jones. Okay. All right. By the way, there, like I said, there has been an update to the teachers that we will be launching Edgenuity and online stuff for all the other classes. I'm sure there's going to be something in there for AP. I'm just hoping that I can just keep doing this and do something minimal over there on that. But also, I looked at College Board website just before I got on here, and they don't have any new update other than to say, they might, or that they're supposed to post something new by the 20th, which is tomorrow, and that they already have a late testing date. Like every year, they have late testing dates. This is like the 3rd week in May. And basically, I think what they're saying is, until they give a new update, that everybody might qualify for the late testing dates with no extra fee. Personally, I don't think that's much of a concession, but that's all they're saying so far.
Another one asking if you're going to be going over the worksheets.
I can go over any worksheet that, like, if you ask me there's a lot in those worksheets. So what I would like to do is go over specific ones you have questions about. And if you ask me those questions now, I'm going to continue with the notes for now, but if you let me know what those are at the end of this session, I'll keep going with those. So yes, I will go over the worksheets, just specific to your questions, not probably the whole worksheet. All right, so now I want to shift over to the extra set of notes that I gave you that you should have picked up when you picked up the big packet. Like before you left for spring break, there were 4 piles, big packet of notes, which we've been going over, a much smaller packet of notes, and then 2 worksheets. So the smaller packet is on titrations. So Zach, if you could go way down to page 15. Yeah, right there. Topic 8. Wait, is this the smaller
This one?
packet? Unit 4, yeah.
Oh, okay, what page?
15. Yeah, right there. So this smaller packet was would really basically the things that are in here that he's showing on the screen there are really what you would have learned, just not in this note format in Chem K, because we did titrations in Chem K. And so really there isn't much new at all in here, but it is a very good review if you have forgotten about the basic concept of titrations from last year. So this is this first part with volumetric analysis, titrations in moles on page, well, it's going to say page 15 because it's the first, that's the only part I copied out for this. But you should absolutely, hopefully, remember that moles equal concentration times volume. Now, I would usually say molarity times volume. What, you know, if I know the molarity and I know the volume, I know moles, because molarity is moles per liter and volume is usually in liters. So moles per liter times liter, those cancel out and we get just moles. And so when you're doing titration, if you think about the substance, if we have a burette, okay, if we have a burette, a graduated burette, and we're then titrating into a flask, okay, in the burette, we generally know the concentration. In here, we have an unknown concentration. When we know the concentration, like the acid or base that we know the concentration of is called the titrant. The acid or base that we don't know the concentration of is called the analyte. So that is in your notes on that page there. And the kind of things that we've already, like, so if the classic titration example is hydrochloric acid mixed with sodium hydroxide. And this, because these are both strong, this goes to completion, and we talk about these being neutralized. And in the neutralization reaction, you're going to get the salt and the water. Okay. Now I haven't put the states in, but this would be aqueous, 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 liquid. But this is our classic titration example or neutralization example, where the hydrogen breaks off of the chlorine, forms with the hydroxide from the sodium to make water, and then the sodium has, the sodium is your positive cation with the chlorine being negative. So that's all in there in your notes. Then task 4.1, 0410. This is a very, very basic neutralization reaction where we're using M1, B1 is M2, B2, moles equal moles. Like, when is it neutralized? When the moles of the acid equal the moles of the base. When the moles of the hydrogen ion equal the moles of the hydroxide ion. That's when we're neutral. This could also be V1, M1 equals V2, M2. It doesn't matter what order they come in. It's because it's a product. So literally for 4.10, you're just saying we have 44 milliliters times some molarity equals 25 milliliters times 2 molar. 2 molar. Now, normally we say, get the volumes in liters, but when this is milliliters on one side and milliliters on the other side, they're going to cancel anyway. So you don't have to convert those when they're both the same unit on both sides. So doing the math here, you're just saying 44M is equal to 50. And so the molarity would be 1.14, something like that. 1.14 molar. That's just the straight algebra there on 4.10 on that task. Any questions on any of that? Anybody? No? Okay. So this again, like I said, should be review, not just from last year with titrations or whenever you took Chem K, but also from what we've already done this year. Now, the thing is if we don't get back in class until April, and of course, some are predicting it's going to be longer than that. Who knows? If we don't get back in class, even if we do, we're not going to be focused so much on labs as getting as understanding labs and understanding things. So the assignment that I loaded into Google Classroom, you should have gotten a remind where I set up a Google Classroom for AP Chem, and in there I put a worksheet that is titration simulation, and I'll reference that at the end of the session here. But that's going to help you with all of the with understanding titrations. Okay. So if you keep going up, go down to page 16. We have types of chemical reactions, acid, base, and redox. Really all we're doing right now is acid and base. Acid and base. So all of this is review. I've already talked about all of this. An acid being a hydrogen donor, a base being a hydrogen ion acceptor. I've given these examples out clearly. If you keep scrolling there, Zach, yeah. I've talked about acid-base conjugate pairs and water being amphoteric. So all of that is reviewed. And then if we go to page 17, again, strength of acids and bases. When you see the arrow going in one direction, that's strong. We're assuming complete dissociation. Again, what defines an acid is the ability to produce the hydronium ion. So when you see something coming over like this, we have a single arrow, and over here we're either getting H plus or we're getting H3O plus. These are the same. These are the same thing here. I mean, really it's this because the water is picking up the hydrogen. This is called hydronium, but the ease with which we can get a hydrogen ion out tells us how strong the acid is. Okay? So when you have a single arrowhead and we're getting hydronium or hydrogen over here, that's a strong acid. When you have as soon as you make that a double arrowhead, now this is weak. This is a weak situation because it's in equilibrium. And only a very little hydrogen ion comes over. Most of it stays. We have very low, very small Ka values. All right. So all of that is on page 17. And then I told you on page 18 already, if you scroll down to page 18, this is, again, one of the most important reactions of acids and bases is neutralization. So I think we can just go straight to the task here. Write a whole formula, ionic and net ionic. So this is task 4.11. And I need the larger board because we're going to write reactions here for potassium hydroxide and sulfuric acid. So potassium hydroxide for the whole thing and sulfuric acid, first you need to know that potassium hydroxide is going to be your strong base. Sulfuric acid is going to be your strong acid. And because you know and recognize that those are strong, we're looking at a single arrowhead to the right. So we have our cation, potassium, is going to join with our anion from the other. So we're going to get KSO4, but what you would need to recognize is that the sulfate ion is -2. So if this is -2, I need 2 potassium, so that's going to be K2SO4. Also aqueous, that's an aqueous salt. And then, of course, the production of water. So this would be your whole formula would look like this, including the states of matter. The whole formula would look like that. And then the complete ionic means split out everything that's aqueous, keep together what's not aqueous. If it's a solid, liquid, or gas, you keep it together. So we're going to have, if it says balanced, they would expect you to balance this. So we're going to have 2 potassiums over here to balance that. And now we have, we're going to need 2 of these here. So we have 2 potassiums, 1 sulfate, 2 hydrogens plus 2 hydrogens is 4 hydrogens, that's 4 hydrogens, and then 2 oxygens here, 2 oxygens here. Alright, so that's the whole one, and then if we split out everything that's aqueous, we have 2 potassium ions, they're aqueous, and 2 hydroxide ions, they're also aqueous. We have 2 hydrogens from H2SO4, they're aqueous, and we have 1 sulfate. Okay, and that's going to go to 2 potassium ions and 1 sulfate ion, and then leave the water together, 2 H2Os. That's your complete ionic. All right. For the net ionic, we're going to cancel like terms on both sides. So we have 2 potassiums and 2 potassiums, so those would cancel. We have a sulfate and a sulfate, so those would cancel. So the only thing we have left are 2 hydroxide ions plus 2 hydrogen ions, forming 2 waters. Now, I understand that we don't need the 2's anymore, and in terms of something balanced, those could be 1's, but if we're giving the net ionic equation from this original, we can just keep the numbers as they are. Now, this does remind, so that's the end of that for like that small set of notes. That's all we needed to do there. Of course, we're going to have more practice with problems and things for that later. But it does remind me that I need to go back to the original set of notes because I forgot something. And that bottom group, yeah, keep right there. Okay, so if you go back with me, if you're following along here live right now, we're going back. What page is that? 12. So go back to page 12 in the original set of notes, and I'm not going to put it all up on the board here. What I want you to understand, and this is very important, is you have to memorize the strong acids. You have to memorize them. So HCl, HBr, so hydrochloric acid, hydrobromic, hydroiodic. HClO4 is perchloric acid. I can do that. I can write out the names. So if you didn't know the names, so let me write out the names. But the reason you have to memorize the strong acids is because you have to know in acid-base equilibrium, you have to know what you're dealing with. If you're dealing with something strong, you know it completely dissociates. If you're dealing with something weak, it's only very partial dissociation, and that changes everything. It changes the whole chemistry. So unless you want to memorize the hundreds of weak acids that there are, all you need to do is memorize the 6 strong ones, because then you know everything else is weak. So HCl, if you didn't remember, HCl is hydrochloric acid. What's the next one? HBr is hydrobromic acid. HI is hydroiodic acid. HClO4 is perchloric acid. HNO3 is nitric acid, and H2SO4 is sulfuric acid. So you need to know that. You need to know everything. You need to know that these are the formulas of the strong acids. These are the names of the strong acids. You have to memorize that. There's no getting around it. But once you do, you know that if you're dealing with any other acid, it's a weak acid. Now, for the bases, it's potentially easier because you can use the periodic table and say anything in group 1. Anything in group 1, sodium, potassium, anything in group 1 with hydroxide is a strong acid. So, KOH, that's a strong acid. Group 2 hydroxides, magnesium with hydroxide, if I said acid, I meant to say base. So these are your group 1 and group 2 with hydroxides. Those are your strong bases. Anything in group 1, except of course hydrogen, it's not a metal, and anything in group 2, those are your strong bases. Anything in group 1, group 2 with hydroxide. Any other base, ammonias, organic bases, things that contain nitrogen, amines, those are all weak. Okay? So, I think that's what I wanted to cover for today. I just want to clarify so for tomorrow, if you could, in the notes, read topic 8E, which is titrations part 2. So that's page 13, 14, and 15. Pages 13, 14, and 15, read those, and do as much of the titration simulation as you can. And so Zach, did I send you that worksheet? If you pull that worksheet up. So he's gonna, this worksheet right here that you see on the screen, I sent you that through Google Classroom. So I know there's a lot of, I'm not trying to make things complicated by any means. I know there's a lot of things going on. There's Google Classroom, not like if we were in the classroom, I would be handing these to you physically. We're not in a classroom now. So think about Google Classroom as where I'm handing you stuff. This isn't for a grade, it's for you to keep on track. And then remind is just the way we communicate, or that I communicate with you for the most part, but you're free to respond to those. And then, you know, this platform here, Twitch and YouTube are the actual teaching platforms.
Did you want you to go over Kristen Jones, page 3?
Page 3. Okay. So, is this what you're talking about?
I'll have to wait for the first one.
I know. Whoever's asking that question, is this what you're talking about? They're not answering?
Not yet.
Because that one's pretty well.
Say not that page.
Okay.
Page 208.
Page 208. Okay. Oh, I see. Some of that's not done. Okay.
Some people want 206, and another person wants 208.
Okay. So I'm gonna. Here's what I'm gonna do. I'm gonna end this session, and excuse me. Let's have a separate session on going over problems like this. So why don't we do that? Let's do that at 1 o'clock. Let's do that at 2 o'clock today, and then it'll get loaded to YouTube, and you can view it later. But we'll do that. We'll do a separate. I'll do a separate worksheet session 2 o'clock today. If you can't make 2 o'clock today, it doesn't matter because it'll be posted later. But that's it for now. One last thing, I didn't want you to think that I don't drink coffee at home. I drink coffee, but see, all my cups at home don't have to do with chemistry. So all of those are at school. So if you were worried about me drinking coffee, I still do it. Zach's rolling his eyes. Not funny. All right. Have a good day.